Hi everyone, welcome to our lab session. I will go over the guided activity as usual. I have a little time today. So let's get to it. In this lab, we'll build upon the framework that we learned in the previous units for statistical inference, both z-test and t-test, as you saw on the lecture videos. The logic of hypothesis testing is being applied here in the same way, but we're learning a new method to compare when your hypothesis requires comparison of more than two independent means. So all about how to apply and employ analysis of variance for testing hypothesis. This might be needed. These are the packages that we'll install. Today a new one is coming up called Agricoli. It's a package developed by a scientist in agriculture that has very cool functions to do the follow-up tests in ways that are pretty simplified. So that's why we're going to use that package in addition to the others that we had used during the t-test session. So let's load them. Don't forget to click and load the packages. Problem 1. The 538 is a website, you should check it out, that tells data-based stories about a variety of issues in politics, sports, science, and health and economics and culture, among others. It's a pretty nice example of how you can use data to tell stories, which I really think is a skill that is so useful, and that, beginning next class, you're going to start practicing. Sorry, beginning this class, you're going to start practicing. So in 2014, they wrote a piece called The Economic Guide to Picking a College Major. The primary question they explored was whether the choice of major is related to salary. They used data from the American Community, from the American Community Survey, 2010 to 2012. Let's load the data set called Major Data to explore this question. Let me clean it up so I can catch the errors. There you go. I loaded Major Data. It's right there. I like to click it every time to look at it. See how it has many different variables. We have ID, we have rank, we have major category, share of women. That? Unemployment rate. What's that? Part-time, non-college jobs rate, bunch of stuff. So, because there are a number of variables that are hard to know what they are, I have this little table describing what the data set is. So, real data set. ID, simply index, simply indexing each data unit. Here it's major. Every major is one. So, every line in our data set is a major. It's a specific major. And the type of variable is just an integer, just a count. The rank is it's the rank of that major based on median earnings. So you have a median salary for each major. And if you have the highest median salary, you're going to be ranked 1. If you're the second highest, you're ranked 2. And that's an integer. Then you have the major, which is just a description, should be a character variable. The major category, however, is a category of major from Carnevale et al. So it groups a bunch of majors into one category. Say there's a bunch of types of engineering majors, and they're all grouped under the category engineering. And that should be a factor variable, because we're going to use it as explanatory variable here. And we have share women. It's women as a share of total. That should be a numeric variable. Unemployment rate. It's unemployed people divided by the unemployed plus the employed in that major. That's numeric, so on and so forth. So you can see what the different variables are. And I'm listing here which particular type of variable it should be. And then you can check by running the str function on major data to see if R gets it right. Because I'm running it in my computer, not in RStudio Cloud, it may be the case that, for instance, an important one, major category does not show up as a factor in your when you're doing your assignment in R. If that happens, you need to change major category to make it, transform it to factor. So everyone that's not mapping up, please adjust just as practice. So you can look at what it should be. Let's say ID, integer. Is that correct? Yeah, integer. Now let's look at rank, integer. Is that correct? Yes, integer. Whatever is not correct, you should learn how to fix that. So let's adjust the ones that do not map up. So major, let's look at major. R is seeing it as a factor, but really that's just our data unit, so it should just be a character variable. So I'm doing major data, that's the name of the data set, little $, name of the variable, and I'm saying that I want that as character. So I do as character, and the input of that function, I just repeat the same thing because I don't want to change the name of the variable. I do the same thing for part-time rate, because part-time rate, let's look here, is numeric, and R is seeing part-time rate as a factor. Not a factor, it's numeric. Then you can use as numeric. So major data, that's a data set, $, the name of the variable you want to fix. You do as numeric, and you copy the same thing in here. Same thing that's there, you copy here. Okay? And there's another one that R got wrong, which is the non-college jobs rate. Non-college job rate. Let's see where it is. Here, non-college job rates, and it's saying that it's a factor, and it's not. It's just a numeric variable. One of the numeric variables we can use. So you need to check if let's say, for our purposes here, really important, that major category shows up as factor. If it doesn't show up as factor, what are you going to do? Well, you're going to write here, major data, then you're going to do $, major category, oops, major category, and then you're going to do the little assignment piece, and then you're going to do as factor, and we're going to copy here. I like to copy so I don't make a mistake by creating a typo or something. And then we recheck the data structure to see if things were changed as we expected. So for example, I changed major to character, and it's now a character variable, so that's good. I changed non-college jobs to numeric. Let's see, non-college jobs is numeric now. It was a factor before. So yeah, so all good. So we did the right changes. Now the research question. Is the choice of major related to salary? One thing we can do is to rank the data based on the median salary. Well, there's already a rank variable, right? So one thing we can do is to order the data set, let's say, based on rank, right? And see that some will have higher salaries than the other, right? It's interesting to see that because then we begin to do an overall look at the data, just to very roughly explore it. So what I'm doing here, I'm getting major data, and I'm asking R to order based on that variable rank. Why? Because the variable rank is it gives a major a number that is related to the median salary, the 50th percentile salary received by people that graduate with that major. Does that make sense? It will get a 1. If it's the one that receives the highest salary, it will get 2. If it's the second best, third best, so on and so forth. Highest median salary, middle of the distribution. All right, so I do major data, and then I just open these brackets, and I say, please order major data based on rank, and keep the other lines all, the other columns the same. And then I do this, and what I see is that number 1 is petroleum engineering. Number 2, engineering again. So there's lots and lots of engineering at the top, and other, what's not engineering is still pretty on the kind of quantitative science type of area. So a quick look suggests that major category might be a factor related to salary. In particular, if we keep going, see, engineering is like showing up on top. There are other things in between there, but engineering is figuring on top. So if you're after deciding your major based on the salary you're going to get, and you are just aiming for high salary, then engineering seems to be a good pick. But we can get a bit more nuanced. So let's keep moving along. Here's the question. Is engineering or are engineering majors more high paid than majors in other categories, as this quick ordering of the data set suggests? So let's quickly see how many major categories we have and how many majors within each category to design our strategy to analyze the data. Maybe we have a more specific question about that. So how many majors? Let's see that. So I'm basically, doing the piping thing. I'm asking R to open up major data, open up this data, and then group by major category, and then summarize by giving me the number of just, the summarized table already asked the mean, the standard deviation. I'm just asking the number of majors in each category, and I'm asking R to print the summary table. So R is printing the summary table here, and we can see that we have a bunch of majors, 16 majors. Some major categories just have one inside, so we can't really use it for testing for differences between major categories. So we need a way to hone in on our question a little bit more. Here's what I'm wanting you to grasp from this piece. You don't need to memorize how to use this code to order things. It's there. If you want to learn it, great. But what I want you to do, to learn, is the process of getting a very messy data set and start using it to answer questions. So if I'm worried about, what's the typical salary that people get, I can get the median salary and then order things according to that. And then you begin to see, engineering seems to be quite on top. So is engineering better than other categories? And then you're looking at the data, oh my gosh, I have like 16 different bunch of different categories here. It's a lot. And some of them don't even have enough majors inside for me to use it as a basis for comparison. Because it's like saying that in a group, there's only 4 people. It's not enough because, you want to have at least some effective metric for examining variation, right? So you definitely, if you have just one, you can't, because you can't get variation if you just have one score. So it just tells you, okay, so if I want to ask the question of this data set, I need to still focus a little bit more. So let's imagine a problem here and focus. Imagine for a moment that you have a cousin, and that cousin is a high school student who is more inclined towards quantitative sciences than engineering, but who is really determined to pick a major that would increase her chances of getting a high salary. Should she sacrifice her wish to go for science majors, such as computer mathematics or physical science, and go for engineering? In other words, are engineering majors better paid than those in computer and mathematics and physical science? Okay, so this is the problem that somebody posed to you. I'm here, I want to decide this thing. I want to get really well paid. What do I do? What major do I pick based on this data? Engineering seems to be on top, but is it really higher than these other things I'm interested in, which is computer mathematics or physical science? So now instead of looking at all of these major categories, we're really focusing on 3 of them. And because we have 3 and not just 2, then we can't use t-tests to figure things out. We're going to have to gravitate towards ANOVA-like tests. So again, this question implicates 1 explanatory variable, major category, and 1 response variable, the salary. So we're going to come back and start diving into the data in order to help your cousin, your imaginary cousin. See you then. Bye-bye.